Let us continue our discussion of electrokinetic flow. Okay. So, I had said that if you have a charged surface, okay, if for example, you have fluid in a channel bounded by walls whose surfaces are charged and that fluid contains ions. The charged surface, if it is positively charged for example, and there are positive and negative ions in the fluid in between the two surfaces, in the bulk of the fluid is neutral because there is no net positive or negative charge. Okay. So, the fluid is neutral. Close to the surfaces, the positive surface charge will attract negative charges close to the surface, and therefore, there will be a net negative charge in the region very close to the surface. I had given you an expression for the charge density. If the surface charge density in coulombs per meter square is QES, okay, capital Q for the surface charge density. The charge density in the fluid close to the surface, the ionic charge density, is given by this expression QES by lambda d times e power minus z by lambda d. Okay. So, where lambda d is the Debye length. Okay. I should note here that this is applicable only for dilute systems. Okay. If the charge density becomes large, then you get more complicated expressions. In a dilute system, this is the expression for the Debye length. Okay. And the length itself is related to the electric permittivity, the energy, the thermal energy, the number density and the electrical charge. Okay. And we had calculated this for one particular fluid with 1 millimolar solution. The electric permittivity is the product of the relative permittivity and the vacuum permittivity, or the dielectric constant and the vacuum permittivity. Dielectric constant is dimensionless, epsilon r. You also have the number density of ions and the electrical charge on the ion square in this expression. So, we had done the calculation of the Debye length for a 1 millimolar solution. 1 millimolar is 10 power minus 3 moles per liter, which is 10 power minus 3 kilomoles per meter cubed. Since we are working in SI units, we should reduce it to all meter cubed, and this is the number of ions per meter cubed. Okay. And based upon this, we had calculated the Debye length. Okay. It varies between about 10 nanometers for a 1 millimolar solution to about 1 nanometer for a 1.1 molar solution. As the charge, as the ionic strength increases, the Debye length, Debye layer thickness decreases as 1 over the number density of ions. Okay. So, this is the rough length scale, and this implies that in most situations the Debye layer thickness will be much smaller than the channel height. Okay, for electrokinetic flows. Okay. I should note that this is a very simplified picture. Okay. In real situations, you have a more complicated configuration. So, if I have a charged surface, okay, there is okay. So, if I have plus, okay, there are usually adsorbed charges, okay, close to the surface, okay, which are immobile. Okay. This is the adsorbed layer, it is sometimes called the Stern layer. It's charges which stick to the surface and cannot move, okay, because of the surface charge density. And then you have diffuse layer which contains diffuse charges. Okay. And in this simplification, we have just assumed that there is no Stern layer. Okay. So, this is strictly not valid. Okay. The surface charge density is often characterized by what is called the zeta potential. At the surface. Okay. And the zeta potential is related to the zeta. okay, is related to the surface charge density by electrostatic charge times lambda d by epsilon. Okay. This is the relation between the surface charge density and the zeta potential. Okay. Strictly speaking, the zeta potential is actually the potential at this location, okay, outside of the Stern layer and within the diffuse layer. Okay. So, this zeta potential is actually a measured quantity which is used to characterize the surface. Strictly speaking, it is outside of the adsorbed Stern layer. Okay. So, in practice, this zeta potential is what will be measured in experiments. In our picture, for simplicity, we will just assume that the decrease we will neglect the presence of this adsorbed layer and assume that the decrease in the surface charge density takes place directly from the surface. That is a simplification. Okay. Strictly speaking, we should actually take into account, we should remove the adsorbed charges from the description and then take the potential in the mobile layer above that surface. Okay. So, this is the relation between the zeta potential and the surface charge density, and I will leave it to you to verify that this ratio actually has the same dimension as electrical potential. Okay. Okay. So, we had this charged surface. Okay. And you have an excess of charges close to the surface, okay, excess of negative charges close to the surface. Okay. And as I said, this charge density QE decreases exponentially over a length scale comparable, sorry, I should write Z here. As a function of Z, the charge density decreases exponentially from the surface. Okay. And so, the bulk of the fluid, okay, over distances large compared to this Debye layer length lambda d, okay, over distances large compared to this Debye layer length lambda d, the fluid is essentially neutral. Okay, there are no net charges. So, this is for the charge density profile close to a surface. What about electrokinetic flow? Okay. So, now what happens is that if I apply an electric field in the flow direction, okay, there is a force density exerted on the fluid. Okay. The force density is equal to E x times the charge density Q e. Okay. Force is equal to the electrical the field times the charge, therefore, force density is equal to the field times the charge density. Okay. So, there is an electrical force that is exerted, okay, and this electrical force density is equal to E x into Q E s by lambda e power minus z by lambda, okay, using the expression that we had for the charge density, that is Q e is equal to minus Q E s by lambda d e power minus z by lambda d, the exponentially decaying profile. Okay. And I can substitute using this expression to get minus epsilon zeta by lambda d square e power minus z by lambda d. Okay, so, this is equal to minus E x epsilon zeta e power minus z by lambda d by lambda d square. This is the force density. So, if charges are separated and localized close to the surface, there is a net charge in the fluid. If you apply an electric field, then you will apply a force per on these ions, and that is effectively a body force on the fluid. Okay. So far we had considered only body force as gravitational force, because it is proportional to the volume. Okay. This is also a force proportional to the volume. So, if I have a particular charge density, multiply that by the electric field in the x direction, and I will get a force density, force per unit volume, okay, for this case. And this force per unit volume is going to generate a flow. If I consider a steady state where there is no time variation, then the conservation equation is 0 steady state mu d square V x by d z square plus F x, force density. F x is the force density, force per unit volume. Okay. So, this is going to generate a velocity. So, 0 is equal to mu d square V x by d z square minus E x epsilon zeta e power minus z by lambda d by lambda d square. I can integrate this 2 times. Okay. Okay, if you integrate this 2 times, you will get V x is equal to E x epsilon zeta e power minus z by lambda d, okay, times z square by 2. Okay, integrate 2 times a constant, one integral will give you z, the second integral will give you z square by 2 plus a z plus b. Now, how do we determine the constants? Okay, how do we determine the constants? So, let us look at this configuration again. Okay. I have this Debye layer close to the wall, okay, where the force density and the charge density are both exponentially decreasing functions. Okay. So, the force density is non-zero only where there is a Debye layer present. Okay. That means that the velocity gradient is non-zero only in that region. Okay. So, if I have some velocity varying like this, okay, there will be a velocity gradient only where there is a force. Okay. If there is no force, there will be no velocity gradient. That means at the center the velocity variation will be 0. Okay. It is only close to the 2 surfaces that you will get a non-zero velocity variation. Okay. If I expand this out over the distance comparable to the Debye layer thickness, okay, if the charge density or the force density in this case, okay, function of z varies something like this, okay, then the velocity will also vary only in this region. Okay. The velocity will also vary only in this region. It should go to the gradient in the velocity should go to 0 far away from this. Okay. So, that means that as z goes to infinity, when z is much larger than the Debye layer thickness, the velocity goes to a constant. At the surface itself, the velocity is equal to 0. Okay. So, these are the 2 boundary conditions that you will use in order to determine the constants. Okay. I made a mistake in this. Okay. It is not z square by 2. So, let me just rewrite that. Therefore, dVx by dz, integral of e power minus z by lambda d is minus lambda t times e power minus z by lambda d. Okay. So, this is equal to minus E x epsilon zeta, okay, e power minus z by lambda d divided by lambda d plus a. Okay. I take one integral, I will get a factor of lambda d above. Okay. If I take a second integral, I will get V x is equal to E x epsilon zeta e power minus z by lambda d plus A z plus B. Okay. So, this is the solution for the velocity field. Okay. So, this is the solution for the velocity field. I have to divide by mu here. Okay. So, back to our discussion. Okay. So, the force density, this one, the force density is varying only over the debye layer thickness, which is of the order of angstroms. Okay. This is varying only over the debye layer thickness, which is of the order of angstroms, where the electrical charge decreases. Okay. That means if the force density decreases only over that distance, that means that the velocity profile will be varying only over that distance. Okay. The velocity profile will be varying only over that distance. In the bulk, the velocity will in general be a constant. Okay. Unless there is a force density, you cannot have a variation in the velocity in this particular case. Okay. So, the boundary conditions, one of them is that at z is equal to 0, Vx is equal to 0, which implies that the constant B equals 0. Okay. So, that is the first boundary condition. What is the second boundary condition? Okay. As z no. Okay. As z is equal to 0, the exponential is just equal to 1. Okay. So, this is the boundary condition at Vx is equal to 0. What happens as z becomes large compared to lambda d? Okay. As z becomes large compared to lambda d, okay, as z becomes large compared to lambda d, this first term here is 0. Okay. This first term here is 0. Okay. So, therefore, you cannot have and I said that as you go towards the bulk, the velocity gradient cannot be 0, has to be 0, because there is no force there. You will have variations in the field variable only where there is a force. Where there is no force, the field variable can be a constant. Okay. The variations in the field variable will happen only where there is a force. Okay. So, this implies that you cannot have a slope of the velocity where there is no forcing, where there is no body force. You cannot have a slope in the velocity profile. That means that for z much larger than the debye layer thickness, right, I should have dvx by dz is equal to 0, which implies that A is equal to 0. Okay. Okay. So, as I go outside the boundary layer, okay, if there is no relative motion between the two walls, okay, if the two walls are stationary and there is no relative motion between them, there cannot be a velocity gradient between these two walls. Okay. A velocity gradient arises only if you have a non-zero stress exerted by the wall on the fluid, or a non-zero or a difference in the velocity between the two walls. Okay. So, the walls at z is equal to 0 and z is equal to h are both stationary. You cannot have a relative velocity between those. That means that the velocity gradient has to be 0 in the limit when the z becomes much larger than lambda d. That implies that A is equal to 0. Okay. So, putting these two together, okay, Vx is equal to Ex epsilon zeta by mu into e power minus z by lambda d minus 1. Okay. I can write this as the slip velocity times 1 minus e power minus z by lambda d, okay, where Vs is equal to minus Ex epsilon zeta by mu. Okay. The slip velocity is positive if Ex is the downstream direction and the zeta potential is negative. Okay. So, that more positive ions are attracted to the surface, and if the potential is in the positive direction, it will result in a positive velocity. Okay. So, that is the meaning of the sign. On the other hand, if you have more negative ions attracted to the surface, then if Ex is positive, the velocity will be positive. because the zeta potential is positive, you have more negative ions attracted, then the velocity will be in the positive x direction. Okay. So, therefore, the flow basically looks like a plug flow, okay, with this slip velocity V s. The flow increases from 0 to its maximum value over a distance that is comparable to lambda d. Okay, it increases from 0 to its maximum value over a distance comparable to the d by layer thickness, okay, and after that it is a constant. So, if you look at length scales comparable to the channel height, let us say if that is 1 millimeter or 1 centimeter, this d by layer thickness is only 1 nanometer or 10 nanometers. So, you virtually will not be able to observe the increase in the velocity from the wall, and the flow looks very much like a plug flow. Okay. So, this is an electrokinetic flow where I have, let us say, positive charges on the surface, negative ions are attracted towards the surface, and then I apply a potential in the x direction, and that generates a flow. Okay. Note that the slip velocity is proportional to the zeta potential, it is proportional to the electric field and inversely proportional to the viscosity. It does not depend upon the d by layer thickness, it does not depend upon the channel height. Okay. So, the slip velocity is only a function of the zeta potential and the applied electric field for a fluid of a given viscosity. Okay. So, that is a characteristic of this. It does not depend upon the height and it does not depend upon the d by layer thickness when expressed in terms of the zeta potential. So, this I had basically expanded out this region, okay, where I got the velocity, okay, the slip velocity going like this and the charge density going like this. Symmetrically, I can expand it out about this. Okay. I will have a similar, okay, if I expand out this region, I will have a similar, okay, expression. Okay. So, in that case, the d by layer thickness will decrease like this and the velocity will increase like this. Okay. It is a symmetric configuration. So, you have a slip velocity at the center and you have two regions where the velocity decreases to 0, where there is force density due to the charges on the surface. Okay. So, what is the slip velocity that one can experience in practice? Okay, because as you can see in this case, the slip velocity is independent of the channel height. The flow rate therefore will be proportional to the channel height. So, given a particular potential gradient and a particular charge localization close to the surface, I will generate a flow whose velocity does not depend upon height, which means that the flow rate is proportional to the height. So, as I make it larger and larger, I will get higher and higher flow rates. Okay. In practical applications, what is the kind of velocities that you would expect, okay, due to electrokinetic flow? So, let us consider an aqueous solution of viscosity 10 power minus 3 kg per meter per second. 10 power minus 3 is the viscosity of water, okay, is in a microchannel of height 100 microns in the z direction between two charged surfaces with zeta potential 30 millivolts. Okay. This is a typical zeta potential of the order of a few tens of millivolts. Okay. the dielectric constant of water is 80. Okay. What is the electric field strength for generating flow velocity of 1 millimeter per second. So, how do we solve this? The electric permittivity epsilon is equal to epsilon naught epsilon r, which is equal to 8.85 into 10 power minus 12 kg inverse meter per minus 3 second per 4 a square, okay, into 80. Okay. The slip velocity is Vs is equal to minus Ex epsilon zeta by mu, okay, which means that Ex is equal to minus mu Vs by epsilon zeta. Minus 10 power minus 3 kg per meter per second into 1 millimeter per second velocity, which is 10 power minus 3 meters per second, that is the velocity. Okay. Epsilon is 8.85 into 10 power minus 12 kg inverse meter per minus 3 second power 4 a square into 80 into zeta. Okay, zeta is the potential. So, this potential is minus 30 into 10 power minus 3 volts. Okay. Volt has dimensions of kg meter square second power minus 3 a inverse. Okay. So, if you do the calculation, you will get 47 into 10 power 3 okay, kg meter second power minus 3 ampere inverse. Okay. You can verify that there will be an ampere in the denominator, there will be a kg in the numerator because these two will cancel, okay, and second power minus 3, okay, because I have second power minus 1 in the second power 1 in the denominator and kg per meter per second, and so these three factors will give me second power minus 3 and ampere inverse. Okay. This is the same as 47 into 10 power 3 volts per meter. Volt has dimensions of kg meter square second power minus 3 ampere inverse. If you recall, we got that from the product of the power, which is the product of the voltage and current. Okay. So, voltage is basically power divided by current. Okay. Power is kg meter square second power minus 3, and so this becomes 47 into 10 power minus 3. So, basically you have to impose a velocity, a voltage difference of 47 kilovolts across a meter in order to generate a velocity, a small velocity of 10 power minus 3 meters per second. Okay. So, this velocity is rather small, okay, even when large electric fields are applied. Okay. So, this is the order of magnitude of the velocity that you would get when electric fields are applied. Okay. So, this is an example of electrokinetic flow. Unidirectional flow, force density is a function of position. In this case, the force density is localized very close to the surface, okay, and because of that the gradient in the velocity is only present very close to the surface. Okay. In the bulk you get a plug flow with a constant velocity, and very close to the surface you get a gradient in the velocity, and we had calculated what that gradient in velocity was. Therefore, if you look on the length scale comparable to the channel height, this looks like a plug flow because the velocity gradient is restricted to a debye layer thickness close to the surface, which is 1 to 10 nanometer. Okay. So, you can generate a plug flow with a slip condition effectively at the wall by electrokinetic flow. Okay. So, this completes our discussion of electrokinetic flows. I will discuss one more example of varying sources and sinks next class, next lecture for the reaction diffusion problem, and after that we will continue with binary diffusion later on. So, I will continue this in the next lecture. I will see you then.